In this section, we're going to talk about two, believe it or not, stranger types of decay. So we've talked about alpha decay and beta decay. There are other isotopes that are also unstable that have even different types of decay than alpha and beta. One of those isotopes is manganese, not to be confused with magnesium. Manganese and magnesium are two completely different things. Mn is the symbol for manganese, and Mn, or manganese 49, is an unstable isotope of manganese. If you wait around long enough, and this is my cartoon version of a manganese 49 atom, something strange happens again, and I want you to focus on this proton here. If you wait around long enough, one of the protons will turn into a neutron, and something that we haven't discussed before. I'm drawing it as a little red circle. And this little red circle is what's called a positron. And the positron is not stable either. It gets fired off into the distance, and the manganese turns into something else as well. I want to bring the positron back again. We haven't discussed it in this class. It's a very strange particle. Basically, it has the size and mass of an electron, but it has the opposite electrical charge. It has a charge of +1, and because of that, it's called a positron. So manganese 49 will undergo a certain type of decay where one of its protons turns into a neutron and a positron. The positron gets fired off into the distance, and the resulting thing that manganese turns into turns out to be chromium. And I won't sort of go over too much detail here, but this that I'm circling here off to the right side of the equation is the chemist's convention for a positron. It looks an awful lot like the chemist's convention for an electron. There's the E for the electron. It has a mass or a weight of 0. The only thing that's different is that the positron has a charge of +1 or +1 instead of the electron having a charge of -1 here. So manganese 49 will spit out a positron, and it will turn into chromium 49. And we can just check the math again. The mass, or the weight of everything we start with on the left side of the arrow, has to match the mass of everything that we end up with on the right side. We started with a mass of 49. The positron weighs nothing, so the chromium has to weigh 49, because 49 plus 0 should equal 49. The number of positive charges we had on the left was 25, because manganese has 25 protons. The number of positive charges we have on the right should also equal 25. The positron has a positive charge. The chromium has 24 positive charges. So 24 plus 1 should equal 25, and it does. And this is basically how you balance these types of reactions. Now, this is a type of decay. The manganese 49 is turning into chromium 49. However, the name for this type of decay doesn't have the word decay in it. It is called positron emission. Why it's called that, there's probably some historical reason, but that is what it's called. It doesn't have decay in the name, even though it is a type of decay. So manganese 49, what you say is that manganese 49 undergoes positron emission. And what that means is that it spits out a positron and it turns into something else. For those of you who are trying to get into the healthcare field, you may have heard of PET scans, and the PET in PET scan stands for positron emission tomography. And what PET scans basically do is, very often what you'll do with a PET scan is the patient will ingest a material that emits positrons, and usually it's a type of sugar. And the person will eat a type of sugar that is emitting a bunch of positrons. The sugar will go to parts of the body that have high metabolism. Sometimes they're looking for tumors, and tumors tend to have high metabolism as well. So you can basically, where the sugar ends up, it will start emitting positrons. The healthcare practitioners, the PET scan people, will have detectors that are able to detect where the positrons are coming from inside of the tissues in the patient's body, and they can basically use that type of information, where the positrons are coming from, to find tissues that have high metabolic activity, and potentially find things like tumors that also have high metabolic activity. and I believe this is an image from Wikipedia showing a PET scan or a positron emission tomography scan. And so this patient has probably ingested this type of sugar that emits positrons at high frequency, and you can see that the person's brain is lit up because the brain typically uses a lot of energy and has a lot of metabolic energy. So that person's brain is emitting positrons, and the detectors can basically figure out where the positrons are coming from. I imagine that a large part of this is the person's digestive system, probably the stomach, but then potentially, again, I'm not an MD, so I don't know how to read these things with any accuracy, but let's just assume that, these other areas that are being lit up, these small areas, could potentially be tumors because, again, the sugars would tend to aggregate in areas of high metabolic activity where they're needed, and then you could pinpoint basically areas that could potentially be tumors. So there's sort of positron emission in real life. The last type of decay that we are going to talk about deals with a little bit of a strange particle as well. So the one that we just talked about was positron emission. This particle here is called a gamma ray, and so this weird figure here is the Greek letter gamma, and the weird thing about gamma rays is that they have a weight of 0, so they don't weigh anything, and they don't have any electrical charge at all. So that's what this lower 0 here means. So gamma rays have no weight and no charge. You may wonder what they are. One way of thinking about gamma rays is that they are kind of like very high energy light. If you remember back a few labs back when you excited the electrons in certain atoms, and I said when they released energy, they released it as different colored light. Well, gamma rays are kind of like light, except that you can't see them, but they are similar in light that they carry energy, and gamma rays have much more energy than visible light. So they're invisible, kind of like UV light, but they're even more, or they have higher energy than even UV light as well. So there are some isotopes that basically release that. So there are some isotopes that are unstable, and what they release are gamma rays. And so the weird thing, if you're sort of following along, the weird thing about this is that if they release gamma rays, and the gamma rays don't weigh anything, and they don't have any charge, then what does the unstable isotope turn into? The fact of the matter is that the unstable isotope turns into itself. It doesn't really change in this case. So this element is a little bit weird. You may not be familiar with it. It's called technetium. And technetium-99, this is an isotope of technetium, can, if you wait around long enough, it will emit gamma rays. But as I said in previous sections, if we're balancing these equations, the weights on the left side of the equation have to equal the weights on the right side of the equation. So if you started out with a technetium atom that had a mass of 99 Daltons, well, you're going to have to end up with something that has 99 Daltons because the gamma ray doesn't weigh anything. And in a similar way, the technetium atom has 43 positive charges. It has 43 protons. The gamma ray doesn't have any positive charges. It has a charge of 0. So the thing that technetium on the left is going to turn into is just technetium again. So you can ask yourself, well, what's the difference? The difference is that this technetium over here on the left had higher energy than the technetium isotope on the right. And where did that extra higher energy go? It went in forming this gamma ray, or this gamma particle, if you want to call it that. So basically, when there is a gamma ray released, the isotope does not change what type of element it is. It doesn't change anything. The mass doesn't change, and the number of protons don't change. And so your book basically wants to have, if the isotope doesn't change, if it still stays as technetium-99 on the left and technetium-99 on the right, how do you actually distinguish between the higher energy technetium atom on the left and the lower energy one on the right? The way that your book does it is that they put this little M in the upper left portion of the symbol as well, right next to the mass. And the M here is supposed to stand for metastable, which means that this isotope of technetium is a little bit stable. It's not quite as stable as this isotope of technetium here on the right. And so this is your book's way of saying, look, this technetium over here on the left, it may look identical to this one on the right, but the one on the left has slightly higher energy. It's a little less stable. If you wait around long enough, it will actually turn into this lower energy technetium isotope, and it will emit a gamma ray. So the gamma emission, which is what it's called, it's not really called gamma decay, although it's perfectly fine to use that term. Gamma emission basically is the easiest one to balance, because whatever isotope you started with on the left, you're going to end up with the same isotope on the right, and the gamma ray weighs nothing and it has no charge. So those are the major types of radioactive decay or radioactive emission that we're going to go over. There are other types of emission and decays, but we'll just sort of leave it at that for now. One other thing that I wanted to point out, I took this slide, this little figure from your book. I think it's a little bit interesting. They basically describe three of the major particles. They describe the particle emitted by alpha decay, the particle emitted by beta decay, and the gamma ray that's emitted. And they basically tell you how far these particles or rays can move through the air. So the alpha particle, which is the heaviest, this is basically the helium nucleus that was emitted. If it's emitted by an atom that is exposed to the air, the alpha particle, that little piece of helium that's spit out, can only move about 2 to 4 centimeters through the air. And this thing that is actually literally being fired out of the atom can't move very far. If it bumps into paper or clothing, that's enough to stop this subatomic particle stop it right in its tracks. Beta particles, so these are basically the electrons that are fired out of the center of the atom. These can travel 2 to 3 meters, so 200 to 300 centimeters, and they can actually penetrate maybe 4 to 5 millimeters, so half of a centimeter into your tissues. And so to protect yourself from radioactive material that is releasing beta particles, you usually need gloves, you need heavy clothing, lab coats. Those types of things will protect you from that. Gamma rays travel much farther. So these things over here that have no mass and no electrical charge, in the air they can travel about 500 meters, so more than 5 football fields in length. They can pretty much pass right through your body, 50 centimeters, or at least portions of your body. And the only way to protect yourself from these types of rays is to use very thick protective equipment like lead shields and very thick concrete. So I just wanted to point this out to you, that gamma rays, they don't seem like much, but they can actually travel very long distances, and to protect yourself from this type of energy, you need very heavy shielding. You need lead shields or very thick concrete. This is another table that I took from your textbook. As I mentioned in the previous slide, there are actually many different types of things that can be emitted from unstable isotopes. And even this table from your book is only a partial list, but it's a little bit more than we've talked about, so I just want to show you some of the other things that we haven't talked about. We talked about alpha particles. Those are emitted by alpha decay, and I said the alpha particles are basically helium nuclei, so this is a helium nucleus. Beta particles are electrons, and that's basically the chemist's symbol for an electron. We talked about positron emission, so there's the symbol for a positron. We talked about gamma emission, there's the gamma ray. Other things can be emitted too, and two of the more common ones that you would have at least heard of are protons, and this is the symbol for a proton and the symbol is H for hydrogen because hydrogen atoms have one proton, and the mass is 1 as well. So that's the symbol for a proton, just in case there are unstable isotopes that emit protons. And there are also some unstable isotopes that emit neutrons, and this is the symbol for a neutron. 1 because the mass of a neutron is 1 Dalton, or 1 atomic mass unit, and a 0 because the neutron has 0 charge. So again, this is just taken from your book, and it's some forms of radiation. It's not a comprehensive list. So to summarize the decay reactions that we've gone over in the past couple of sections, what I want you to be able to do is I want you to be able to find the missing value in any of the types of decay reactions that we've gone over in this unit. So if I show you an alpha decay or beta decay problem, or positron emission or gamma emission problem, you should be able, and I hide one of the pieces in the reaction, you should be able to figure out what the missing piece is. And as an example, here is a positron emission reaction that I showed you previously. This is manganese 49 spitting out a positron and decaying into chromium 49. So this is the complete reaction, but it is possible that I could hide a piece like this, and I could put a question mark there, and you should be able to figure out what the question mark is using a periodic table and using the rules that we went over in these past few sections. I don't have to hide just this one, though. I could hide this over here, and I could tell you that manganese 49 decays into chromium 49 plus something else. What is the something else? Alternatively, I could hide the beginning isotope and say, look, there's some isotope that's unstable that decays into chromium 49 and a positron. What is it? And you should be able to use the rules to figure that out as well. I can hide any one of the pieces in these types of equations, and you should be able to use relatively straightforward math and your periodic table to figure out what the missing piece is. One final thing that I do want to point out, if you want, you can certainly memorize what an alpha particle is and what alpha decay is and what a beta particle is and what beta decay is, and the same thing for positron emission and gamma emission. You certainly don't have to. I don't expect you to memorize these. I forget them myself, especially if I, as this unit passes, this stuff leaks out of my head. And if you want to memorize it and it helps you to work through these problems, that's perfectly fine. But you should be able to do any of these problems without even knowing what alpha and beta decay are and what positron and gamma emission are. All you really have to do is balance the tops of the top numbers, and you should balance the bottom numbers, and it won't matter what the names are.